if we only rely on empirical findings. So the purely empirical approaches will not really lead to scientific progress. What we need instead are theoretic models. They should be reasonable and they should give us a high explanatory power. And then in turn, once we have these models, we can go back into the lab, perform experiments in order to verify these theoretic models. Now, what's currently dominating instead of this more scientific approach is a more engineering approach, and I would like to contrast this as the experimental versus the theoretical approach. So the more scientific approach tries to answer the why question, whereas the engineering approach more asks how. How can I get good results on the test collection that I have currently available? But on the other hand, in science, we are more interested in explanatory power. The scientific approach forms the basis for a broad variety of approaches, whereas the engineering approaches, well, they offer potential for some further improvements in limited settings, and you can observe this when you look at how papers from Sycamore CIR are cited. Then usually they are cited for the next 1 or 2 years, and then most of the papers are forgotten. So the engineering approaches, they are mostly very short-living, whereas the theoretical models are more long-standing. And also, what we can say, looking at our field, especially in computer science, looking at all the publications from the last 50 years or so, we can say there's empirical evidence that the most important contributions to our field are not the experimental ones. Instead, it's only the theoretic approaches that really bring our field forward. It may not really be the case for IR, but I think this is, well, I come to that at the very end. So following a more scientific approach means try to reach 4 goals. First, we try to reach a better understanding. We want to be able to perform better predictions, but we also should be able to understand the limitations of our knowledge. I think that's very important. And finally, of course, once knowing the limitations, we want to broaden the view. Better understanding, well, if we look at our field, then there are very few verifiable theories that we have so far. So starting with the probability ranking principle, we have got a number of relevance-oriented probabilistic models that are verifiable. We have language models, and another important example are the term weighting axioms developed by Hui Fang. And I think there are only a few more really solid theories that we have in our field. And in order to illustrate what I mean by better understanding, let me give this simple example of the classic binary independence retrieval model, where the core of this model is the independence assumptions of this type, where it is assumed that terms are distributed independently in the relevant and in the irrelevant documents. But this is the assumption, and the interesting question is, did anyone ever check this? Well, in former times we didn't have enough queries to do real studies of this kind, but now we have larger collection with more queries, but I'm not aware of any study that really tries to find out to what extent this assumption really holds on a collection. So probably the quality of this model for a collection depends on the extent to which this assumption is fulfilled. But whether it has been done or not, at least this model shows me that it is possible, in principle, to verify the underlying assumption. So this is a rather transparent model. Contrast this with the currently popular learning to rank approaches, which are, at least from my point of view, rather intransparent models. just take everything you have, all kinds of features you can think of, throw it in your learning approach, and in the end, it will give you good results. But what have we learned from an IR point of view? Well, from a machine learning point of view, there are some interesting issues, but from IR point of view, we learn nothing at all. And so we should try to get a more transparent view of what's going on. For example, one simple example on looking on what's going on is what one of my students did. He computed the probability of relevance for different pairs of TF and IDF values. So here we have the document frequency, and here we have the within document frequency of terms, and as expected, the highest probability of relevance we get for terms that have a low document frequency and a high relative within document frequency. So, and we also see that the within document frequency doesn't have such a big impact on the probability of relevance, whereas the IDF value has a much stronger influence on probability of relevance. Now, this student did some work on language models where it is said that, well, you use IDF only for smoothing, and in fact, the most important thing is the within document frequency, but these observation contrasts at least this classic explanation. Also, when you compare different collections, for example, then we see that in INEX, the decline for a higher IDF, higher DF value, so when the IDF value goes down, then the probability of relevance goes down more drastically than was the case for TREC. And so the question is why this is the case. One possible explanation would be that it's the interpretation of relevance, whereas TREC uses a rather loose definition of relevance. A document is relevant if there's anything relating to the query, whereas in INEX we use a more strict definition of relevance, and this might be a possible explanation for this feature. So what, this year SIGIR, I only found one paper that tries to take this approach, but I don't want to go into the details of this. Well, besides getting a better understanding, we want to do better predictions. So for that, what we should do, where we could start, is first we should define a parameter set for describing the currently available collections consisting of documents and topics. Then we should characterize existing test collections by means of this parameter set. We could also try to regard sub-collections, and then based on these observations, we could design new collection and then try to analyze the correlation between the parameters and the resulting quality with regard to the application of specific methods. And then usually we will notice some deviations. So maybe our parameter set was not sufficient. We need other parameters. So we go back to step one, define additional parameters in order to develop better models for predictions. Next major point is limitation of current knowledge. Well, in fact, if we look at the field of IR, I would like to use this analogy to our knowledge about Africa about 300 years ago. So only the coastal area, or mainly the coastal area, was known, and very little was known about the inner part of Africa. So, and in fact, in information retrieval now, whenever someone comes up with a new collection, we are in terra incognita, and we would like to make some prediction. Well, we could say, okay, maybe we could try with some interpolation. We know what's here and what's here, so we can try to do some interpolation in order to make a prediction what might be here. But of course, from what was known at this time, one could easily make the prediction there are no mountains reaching 5,000 meters in Africa, because we haven't seen anyone, and using interpolation, there can't be anyone, but of course later the Kilimanjaro was discovered, and the same thing would be, for example, about large lakes like the Lake Victoria. So interpolation is a very unreliable means. And what's even worse is extrapolation. So from what we saw here, we can hardly make any predictions what might be here in Arabia. But the question really is, how can we define the boundaries of current knowledge? How can we really specify what we know and what we don't know? I think this is very difficult at the moment. Finally, of course, we should try to broaden the view. We should consider context, and one possible direction, other possible direction would be the retrieval of complex objects. But I have to conclude now. Well, overall, I think I have convinced you that IR is still in its scientific adolescence, or even one could say it in its infancy from a scientific point of view. The currently prevailing engineering approaches are fine for tuning specific applications, like, for example, web search. That's okay, this engineering approach. Google and Bing and so on, they are doing the right thing, but for the broad range of IR applications, we need more scientific approaches. We cannot start whenever someone comes up with a new collection, for example, in a company or so. You cannot say, well, let's build a test collection with this, and then after 2 years I can tell you how to do it. Instead, we need scientific methods in order to predict which method would be the right one for getting good results for this application. That's what we should be aiming at. Thank you for your attention.